Hello students, we are going to talk about some new concepts and the concepts of electrostatic potential or electric potential difference, simply voltage. We are used to voltage in our daily lives like a 12 volt battery, 110 volt or 220 volt at home, 1.5 volt flashlight batteries and so on. In this picture you see this voltage produced across a human heart known as electrocardiogram ECG. So, this is the use of voltage in medical science. This voltage is nothing but electric potential difference. Now, students, let us understand very clearly what is potential difference through a very small video. Imagine you have two beakers filled with equal amounts of water. They are connected by a pipe at the bottom. If you observe the two beakers, do you think will water flow from any of the beakers? No. The water level is same in both the beakers. There is no water flow. Now, let me give you some task. Without changing the amount of water, can you make water flow from beaker 2 to beaker 1? Answer my question again. You need to make water flow from beaker 2 to beaker 1, but you are not allowed to change the amounts of water. So, you cannot add or remove the water from any of the beakers. Then how will you do it? Yes, it is very easy. Just raise the height of the second beaker. So, that is why the water will flow from second beaker to first. Then what happened exactly here? What is the factor that made water flow? Yes, the factor is height. Yes, you can talk about gravity or pressure difference also, but in simple terms the factor is height difference, what causes the water flow from second beaker to first. In an exactly similar way, for electricity to flow, there has to be some factor. Let us see. Suppose we have a copper wire. Will electricity flow through it? Clearly not, because there is no factor triggering it. So, what is the factor that triggers electricity to flow through it? And the factor is potential difference. What is the potential then? Have you heard it before? What is potential? Yes, we know potential energy, that is the stored energy when an object is at rest. When you are holding a ball, it has potential energy. When you drop it, it is converted into kinetic energy. Kinetic energy is the energy when an object is in motion. Similarly, there is the concept of electric potential energy. It is the stored energy that a charge has. It describes how much stored energy a charge has, just like holding a ball. A negative charge near negative charges has high potential energy. If left free, the charge will be repelled by the negative and move towards positive charge, just like the ball moved towards earth. Then what is potential difference then? It is the difference of electric pressures between 2 points may arise from the battery consisting of cells, and this potential difference is referred as voltage. So, now students, let us see in detail what is electric potential energy. So, first we will start electric potential energy, and before going to start, let us clear our ideas on work. Suppose you are lifting some weight and moving forward, okay? Then in this case you are doing no work, that means work is 0, no work. Why? Because you are applying force against gravity and displacement is forward. So, angle between force and displacement is 90 degree. So, you know the formula W is equal to F dot S. So, F S cos 90, that is 0. This is the first case. Second case, suppose you were standing and holding a box for an hour, still you are doing no work because you are not moving. So, displacement is 0, work done is 0. In third case, you are pushing a box while moving. Okay? So, your force and displacement are in same direction. So, angle between them is 0. So, W is equal to plus Fs. That means, you are doing positive work. So, energy is increased. In fourth case, the block is moving forward and you stop this block. That means, this force and displacement are in opposite direction and angle between them is 180. So, W is equal to work is equal to minus Fs. That means, you are doing negative work. So, energy is decreased. In electric field, work done W is equal to F dot ds, and here the concept of charge. So, force is equal to Q into E dot ds, that is the work done. Now, let us study in detail what is electric potential energy. Let us imagine, suppose imagine you have a charge plus Q1 here. Plus Q1 here. At a distance r apart, you have another charge that is plus Q2 at point P. It is very clear that in order to bring them together, in order to bring them at a distance r, I have to do work, because these two are positive charges and they repel each other. So, I have to do more work to bring this charge from infinity to this distance. That means, it is like a pushing in a spring. Suppose this is plus Q1 charge and this is plus Q2 charge, and this is like a compressed spring. Okay? When I release this spring, I get the energy back and they fly apart again, because these two are positive charges. So, I have to do work, that I call electric potential energy. Then how much work I have to do? Let us see. Well, when you place plus Q1 charge, it does not take any work to be placed. But when I come from very far away, that is infinitely far away, and bring this charge plus Q2 at this distance, I have to do work. That means, I have to push, and when I get closer to this Q1 charge, I have to push more, because Q1 will repel this charge Q2. Suppose I am here, Okay. So, the force due to repulsion, that is electric force, is in this direction, and my force, that I means here, that is external agency or electric generator, what you can say. The same force I will apply, that is external agency, and the work done W is equal to force due to external agency dot dr integration from infinity to r, because I am bringing this charge from infinity to this distance. I can write also in the form of F electric, that is integration from r to infinity dot dr. See, I am doing positive work here. Why? because my force and displacement are in the same direction. So, that is why, because I am pushing, so my force and displacement are in the same direction, that means I am doing positive work here. See, in this case I can write, just flipping over infinity to r to infinity, I can write this. So, work done for these two cases are same, okay? Because F external and F electric are same in magnitude, but opposite in direction. So, I will take this integral for calculation purpose, as it is very easy to calculate. See, electric force and also displacement are in same direction, because the q1 will be repelled and the force of repulsion is also in this direction. So, as force, electric force and displacement are in the same direction, so angle between them is 0. So, cos 0 is 1. So, that is why I will take that means work done W is equal to, by putting the Coulomb's law, that is Coulomb's formula, force is equal to q1 q2 upon 4 pi epsilon naught integration of r to infinity dr upon r square. Okay. The students, here what is the need of integration? Why we are not using the direct formula of work, that is force into displacement? Because when you are pushing, that means force is increasing. Okay. So, force, both force and displacement are variable, then which force you will take to calculate the work done? So, that is why we are taking a very small displacement dr here, and in this small displacement force is same everywhere. Okay. So, now we are permitted to put formula W is equal to force into displacement. Okay. So, in order to get total work done, I have to integrate, that is F dot dr. That is why we are integrating the, where the integration is needed. So, integrating, we will get q1 q2 upon 4 pi epsilon naught minus 1 upon r limit r to infinity. So, that is equal to q1 q2 upon 4 pi epsilon naught minus, that is 1 by infinity minus 1 by r. 1 by infinity is 0. So, minus times minus is plus, then q1 q2 upon 4 pi epsilon naught capital R. This is nothing but our electric potential energy. This has the unit of joule and this is a scalar quantity. Okay. Let us define what is electric potential energy. Electric potential energy of a charge at this point, at a point in the presence of another charge, is the work done in bringing this charge from infinity to this point without acceleration. Remember this word, without acceleration, because if acceleration is there, then velocity will be there and kinetic energy also increases. But we want to store only potential energy. That is why I have to do work without acceleration. See here, if both q1 and q2 are positive, then energy will be positive. If one of them is negative, then energy will be negative. So, this energy, our energy is very sign sensitive. Okay. Now, I want to convince you yourself that suppose I did not come along a straight line and I come from a very crooked way, that means in this way I will come and finally I reach this point. Okay. I will not come the straight line, in the straight line I will come in a very puzzled way and finally I reach this point. Then what is the work done? The work done is same as it is. Okay. So, as we are dealing with conservative force, you know the gravity is also a conservative force. So, That means, when we are dealing with conservative force, the work has to be done in going from one point to the other is independent of the path, and that is a difference, that is the definition of conservative forces. Similarly, electrostatic forces are also conservative forces. So, it makes no difference whether I come along a straight line or in a very crooked way or puzzled way. Okay. Next, we will see what is electric potential. Now, I turn to electric potential. For that, I start off here. Suppose I have a plus q charge and at a distance r apart, I placed plus small q, that is a test charge plus q at the point P. Then by definition, electric potential energy U is equal to capital Q small q upon 4 pi epsilon naught r. Now, I want to introduce electric potential. This potential is the work done, that the work I have to do in bringing the charge q, the charge test charge q from infinity to this point P. So, that means work done per unit test charge is called our potential. Work done, work per unit charge is called the electric potential, and this work done is stored as electric potential energy. So, I can write energy per unit charge, that is our electric potential. Putting the value of U here, I can get, that is B potential at point P is equal to q upon 4 pi epsilon naught r. This small q has disappeared here. So, this is the expression of potential at point P due to the source charge capital Q. Energy has the unit of joule and potential has the unit of joule per coulomb, or generally we call that is volt, named in the honor of Alessandro Volta. Alessandro Volta, an Italian physicist. Okay. So, students, what do you observe from this formula? That when R goes off, potential will become lower. So, I could make a graph here, that is potential versus R, then the graph will be like this, that is V is inversely proportional to R. Because when R tends to infinity, V is equal to potential is 0. That means, at infinity potential is 0. We are taking generally the potential of earth is 0 for our convenience. Now, let us see a figure, that computer generated figure of potential for a single charge. See, this figure shows a computer generated plot for the electric potential VR of a single point charge in the xy plane. The magnitude of potential increases as R tends to 0 and is plotted vertically. Okay. So, students, see, if the charge q is positive in the space everywhere, then the potential is positive. If the charge q is negative in the space everywhere, the potential is negative. So, near the positive charges the potential is positive, near the negative charges potential is negative. So, electric potential can be negative also, and when you are very far away, then the potential is 0. Okay. Now, we do have a collection of charges. Okay. Then what is the energy of this system? Let us see a 3 particle system. First bring Q1 charge. You have to do no work for this Q1 charge because you do not feel any force of attraction or repulsion there. Now bring Q2 charge, then you have to do more work because Q1 will repel Q2. Okay. Then bring another charge Q3, then you have to do more and more work because both Q1 and Q2 repel Q3. So, for Q1 there is no work, and when you bring Q2, then due to Q1 for Q2 the energy spent, that is U12. So, U12 is equal to K Q1 Q2 upon R. R is the side of the triangle. And for Q3, due to Q2, energy U23 is equal to K Q2 Q3 upon R. And due to Q1, for Q3, energy U31 is equal to K Q1 Q3 upon R. And the total energy is the sum of all energies. Okay. You are seeing here, suppose I have a negative charge, then the energy will be positive for positive charges and energy will be negative for negative charges, and the total energy is the sum of all these energies. Okay. So, students, this energy belongs to this system. Suppose you have n particle system and there are capital N number of pairs, then capital N is equal to half n whole into n minus 1. Suppose n is equal to 3, that means you have 3 particle system, then capital N is equal to half 3 into 2, that means 3 pairs, that is U12, U13 and U23. So, the total energy is sum of all energies. Suppose n is equal to 4, then you have capital N is equal to half 4 into 3, that is 6 pairs. Okay. So, students, never confuse between the electric potential energy U and the electric potential V, because suppose you have a collection of charges, then the electric potential energy U has only one value and this belongs to the system of energy, but electric potential is different from there to there to there. That means, suppose when you are very close to this positive charge, you will get positive potential, and when you are very close to negative charge, you will get negative potential. So, do not confuse the two terms, that is electric potential energy and electric potential. So, students, we discussed about electric potential energy and electric potential. Electric potential is the indicator of the location, but electric potential energy is the work done in bringing the charge from infinity to that point. So, that work done is stored as an electric potential energy. My dear students, this happens in our life also. So, how much effort you will put in acquiring knowledge, that effort will be stored as potential energy, and that energy will give you result in the future in your life. So, my dear students, study well and store it as potential energy. We will see the what is the line integral of electric field, and we will find the relation between electric field and potential. So, to find line integral of electric field, suppose I have a position at point A and I have another position at point B, and I specify the potentials at point A, that is V A, and at point B, that is V B, and the distance is R. By definition, work done W is equal to get to A, that is from A to infinity, force dot dr. Dividing Q charge, we get, that is, this is potential at point A is equal to force per unit charge, that is E electric field E dot dr from A to infinity, and similarly at point B, Vv is equal to B to integration from B to infinity E dot dr. The potential difference between the points A and B is V A minus V B is equal to integration from A to B E dot dr. Now, also I can write that in some books there is written also, that is V B minus V A is equal to minus integration from A to B E dot dr. Okay. This is exactly the same. Okay. Now, I want to change the dr in a symbol, that is dl. So, when I go from A to B, this is the potential difference. Suppose I will go in this way, then also the potential difference V A minus V B is not going to change, it is the same as it is. So, I will take a small element dl, it is a small vector dl, and the electric field is in this direction E vector. Then I can write that V A minus V B is equal to from A to B E dot dl, or V B minus V A is equal to minus of A to B E dot dl. Just dr is replaced by dl, and this is the line integral of electric field. Okay. You can imagine, suppose a plus q charge at position q, okay, and this q charge wants to go from A to B, as the electric field is in this direction, that is from higher potential to lower potential, the q charge wants to go. In a gravitational field, the matter, suppose like a chalk here, when I release with 0 speed, then it goes from higher potential to lower potential. Similarly, that in analogy, positive charges will go from higher electric potential to lower electric potential, and negative charges will go from lower electric potential to higher electric potential. This is the unique in electricity. Okay. So, protons will go from higher to lower potential and electrons will go from lower to higher potential. So, when these charges will go from A to B, that is from higher potential to lower potential, some energy will be released. How much energy? The work done or the energy to get to A is equal to Q into VA, and the work done or the energy to get to B is equal to Q into VB. So, the change in potential energy, it is UA minus UB, is equal to Q into VA minus VB. From work energy theorem, we know that the sum of kinetic and potential energies is conserved. So, when we are dealing with conservative fields, that is when I drop a marker also here, then it will go from higher potential to lower potential and it is converted into kinetic energy. Similarly, this difference is also converted into kinetic energy. So, I can write this is equal to Kb minus Ka, that is kinetic energy at point B minus kinetic energy at point A. This is really the work energy theorem and it is the conservation of energy. Now, I want to discuss with you the connection between electric field and potential. Imagine the electric field in space here. Okay. And I have a charge Q at point A. So, I start at point A and I walk around and I will return to the same point A. Then from the relation VB minus VA is equal to minus of A to B E dot dr. So, at the same as it is the same point, so VA minus VA is equal to dl minus A to B E dot dl, that is equal to 0. So, I can write here that is E dot dl, the integral is from A to B is equal to 0. So, I can put a circle here that represents that this is represents a closed line, not a closed surface, but it is a closed line. Okay. So, this is the case when you are dealing with static conservative fields. So, students, from this relation you observe that the potential is the integral of electric field. Then it is obvious that the electric field is the derivative of potential. Let us see. So, for that imagine a charge plus q here, and at a distance p, at a distance r, at a point P, the electric field is E vector, as the electric field direction is outward, E is equal to q upon 4 pi epsilon naught r square r cap, where r cap is the unit vector in the direction from plus q charge to point P, and the potential is q upon 4 pi epsilon naught r. Now, we will see what is the relation between the two. So, this is the expression of electric field and potential here. Electric field is a vector quantity and potential is a scalar quantity. Now, taking derivative of potential with respect to r, that is dV by dr is equal to q upon 4 pi epsilon naught 1 upon r, derivative is minus 1 upon r square. To get electric field, I need a vector, that is why I will multiply r vector both the sides. Then you see this is E, this is not E, this is minus E, this is minus E. So, derivative of potential is minus E, not plus E. Okay. So, electric field is equal to minus dV by dr r cap. It is very important relation, you must remember. Taking derivative of taking magnitude of electric field in x direction, that is E x is equal to del V by del x when y and z constant, like this in y and z direction. So, the unit of electric field is, that is volt per meter, volt per meter. Earlier it is Newton per Coulomb, but now the unit of electric field is volt per meter. In Cartesian coordinates, electric field E vector is equal to minus taking common, there is del V by del x x cap plus del V by del y y cap plus del V by del z z cap. So, I can write as E x I cap, because E x is minus del V by del x, I cap, because I cap here it is a coordinate system x, y and z. In x direction, that is I cap, in y direction it is j cap, and in z direction it is k cap. So, I can write E x I cap plus E y j cap plus E z k cap. So, this call D represents partial derivatives. That is, when I do derivative with respect to x, then y z will remain constant. When I do derivative with respect to y, x z remains constant, and when I do derivative with respect to z, x y will remain constant. So, I would write electric field E vector in the form of minus grad V, or in symbolical form E vector is equal to minus gradient of potential V. This negative sign indicates that electric field points from a region of higher potential to lower potential, and the gradient points in the direction of maximum increase of the potential V. Suppose you have a mountain here and here it is the ground, then at mountain it has higher potential and in the ground lower potential, then the electric field will go from higher potential to lower potential, and the gradient points in the direction of maximum increase. So, that is the direction of gradient of V. So, it is lower potential means high negative potential. Okay. So, here high positive potential, here high negative potential or low potential you can say. So, positive charges will move from high to low and negative charges will move from low to high potential. In a battery also we can see this is positive and this is negative, then electric field points in the direction of positive to negative, higher to lower, and gradient is in this direction, they are opposite to each other. So, that is why they are minus sign. In an uniform electric field you see in an uniform electric field, suppose in 2 points potential is V1 and V2, in a uniform electric field E is equal to minus del V by del R. Here is the electric field direction is like this and distance is R. So, that the change in potential del V is V2 minus V1 and distance is suppose D. So, I can write here E is equal to V1 minus V2 upon D. So, V1 minus V2 is equal to E into D. This is the case in the uniform electric field. Let us solve one example here. Suppose you have the potential in xy coordinates, that is A is equal to x square A whole into x square minus y square, then what is the electric field strength? Find out this problem, find out electric field. Yes, that is E x is equal to how much? That is minus del V by del x. So, this is minus 2 x and U I is equal to minus del V by del y, that is equal to 2 y. So, electric field in the vector form is E x I cap plus E y j cap. That is why I will get 2a taking common, that is minus x I cap plus y j cap. This is the answer. Okay. Now, let us see what is the potential due to a charged cell. The potential due to a charged cell or a conducting sphere. Potential due to a charged cell. Imagine a conducting sphere and the charges are distributed on the surface. You know that the sphere has radius capital R and a distance small r at point P, you have to find out the potential. In case 1, suppose P is outside the sphere, then what is V? We know E is equal, electric field is equal to Q upon, and the charge is Q charge is distributed. So, Q upon 4 pi epsilon naught R. So, from the relation dV is equal to minus E dr. So, V is equal to minus integration of E dr. So, minus Q upon 4 pi epsilon naught 1 by R integration, that is minus 1 by R square. Minus times minus is plus. So, we get V outside is equal to Q upon 4 pi epsilon naught sorry, E is here r square. So, potential is minus 1 upon r. So, potential is 4 pi epsilon naught r. This is the expression of potential outside. In second case, suppose the P point is on the surface, then small r is equal to capital R. So, V on the potential on surface is equal to Q upon 4 pi epsilon naught capital R. Now, in third case, you know that electric field inside the conducting sphere is 0. So, inside the sphere electric field is 0. That means dV is equal to 0. So, V is constant as same as the potential on the surface, that is Q by 4 pi epsilon naught capital R. Then I could make a graph here, that is potential versus R. Then from inside to the surface, that is potential will remain constant, and when I go outside it will decrease as V inversely proportional to R. Okay. So, this is the graph for V versus R, and this is here is the R on the surface, and here inside and here outside. Next we will find out potential due to a non-conducting sphere, due to a charged non-conducting sphere. Imagine a charged non-conducting sphere, that charges Q are distributed volumetrically inside the sphere, and the radius of sphere is capital R, and at a distance r at point P you have to find out the potential. Similarly, the case 1 is V is, that is Q upon V outside is Q upon 4 pi epsilon naught small r, and on surface V potential Vs potential on surface is equal to Q upon 4 pi epsilon naught capital R. And in third case is most important, that inside the charged non-conducting sphere, what is the potential? See, you know that as charges are volumetrically distributed inside the sphere, so we have to find out the volumetric charge density rho. We know that rho is equal to charge per volume. So, Q is equal to rho, and volume of the sphere is 4 by 3 pi capital R Q. That means, here I will find, and we know the expression of electric field inside the non-conducting sphere is rho small r upon 3 epsilon naught. Okay. So, putting the relation dV is equal to minus E dr. So, V is integration from, that is, suppose here, so this is the small r, this is the point P, and inside the sphere, then I will find out, I will take integration from Vr inside to surface Vs is equal to minus E minus integration of, here I will take integration from small r to capital R E dot dr, and the expression of E is rho r upon 3 epsilon naught dr. Then this is Vs minus Vr is equal to minus rho upon 3 epsilon naught, this is r square integration from r to capital R. So, that is minus taking here, that is Vr minus Vs is equal to rho upon 3 epsilon naught, this is capital R square minus small r square. So, Vr is equal to Vs plus, then what is Vs? So, Vs is the expression, see, Vs is q upon 4 pi epsilon naught capital R. Putting the value of q, that is rho 4 by 3 pi r q, here pi epsilon naught r, pi cancel, and here 4 cancel, 1 r cancelled. So, we get rho r square upon 3 epsilon naught. So, that is Vr is equal to Vs, that is rho r square upon 3 epsilon naught plus rho r square upon, here 2 is there, here sorry, here r square by 2. So, 2 is there. So, that is 2 into 3 epsilon naught minus rho small r square 2 into 3 epsilon naught. So, rho upon 3 epsilon naught taking common, that is 1 plus half, that is 3 by 2 capital R square minus 1 by 2 small r square. This is the expression of potential inside the sphere. This is very important relation, you must remember, because we are going to use a lot in competitive examinations. So, I could make a graph here. If I go to center, then we see that V potential at center is 3 by 2 times, that is 1.5 times of potential on the surface. So, when I make a graph, that at the center it is maximum, and when I go outside it will go on decreasing in this way, and at the surface it has fixed value, and outside as B inversely proportional to R it will go on decreasing. See, at the center it is Vs and it is Vc. So, at the center this is 1.5 times of potential on the surface. So, students, we discussed, we found the relation between electric field and potential, and we discussed about the graphs, that is the V versus R graph for both charged conducting sphere and charged non-conducting sphere. You must remember these are very important graphs because those are always asked in the examinations. So, you should remember. Thank you.